Welcome back. Now, we are going to look at some of the ideas that we learned from thermodynamics, and also we understood the different kinds of Newtonian way of looking at the trajectory of the atoms, and also looking at the Lagrangian way of looking at the motions. So, if you look at all these parameters that we looked at in the different kinds of ensembles, we have to understand the particle motions in 1 dimension, 2 dimension, and also in 3 dimension. So, the new topic that I want to introduce, and we will get into more details, is the computational method for molecular dynamics simulations. So, let us come up with basic ideas about the motion of particles and things like that, and then we will go into what we call is the basis for all numerical methods to calculate differential equations. We want to look at the differential equation. Most of you must have done basic course in calculus. So, you need to brush it up and see where we go with the motion, equation of motion, and the numerical methods to calculate differential equations. So, I am just going to take few minutes of time, set you up with the basic concepts of motion. So, let me write some of the equation, remind you of them, and then we will get into the dynamics part of it, where you are going to then be introduced to different computational algorithms that you have to use in order to solve second order differential equation, which is Newton's equation of motion. So, let us look at some of the equations now. And so, if you look at your screen, I am going to start very basic. So, those who do not have any background should not feel that I am talking something different. So, we start with the basic concept of speed. So, if you look at a point A and you go to point B, and let us say this is a distance delta x, which was done in time delta t, then you can come up with the speed. Number 1 is speed is equal to distance over time. And this is irrespective of the direction, which direction you go, it does not matter. But as soon as I put an arrow here that has a not only direction, but it has a speed, but also direction. So, there is a motion with direction from A to B, then we call it as velocity. And velocity normally is defined by v with a arrow on top, which says it is a vector quantity with a direction delta x over delta t. Now, with that understanding, we are looking at the average distance and average velocity. All right. So, now if I look at acceleration, then acceleration becomes the change in the velocity. So, if you look at v velocity v 1 and v 2 minus v 2 over t 2 minus t 1 time difference, then it will become delta v over delta t, and that becomes acceleration A. Now, that you understand that, now differentially what you can say is there is x, which is the position, and then you have v, which is velocity, and A, which is acceleration. So, if you look at these three quantities in differential form, you can say x is x 0, that is the starting point. I will just take starting point at this point, boundary condition, and I will extend it to a generalized expression later. But then dx over dt is the velocity, distance over time, and these are exact differential, and then you get d square x over dt square. These are not partial differential, these are the total differentials here. So, now you can see these three things. So, once we define that, then we can, now we are ready to define motion of a particular particle, and that is what we are trying to do, motion of a particle. All right. So, now if we look at the motion of an arbitrary particle, then we can take any direction. So, this is t and this is x, and the particle can go anywhere from that. So, this could be x 1, x 2, x 3, and then so on and so forth. So, we now can understand 5 different locations of those particles. So, if I have to now look at x, okay, so now we are going to look at x and differentiate it. So, let us say x is defined by an equation 8 minus 6 t plus t square, and t is the time, then velocity will be dx over dt. We do that, then we have 8 is gone because that is the differential, minus 6 plus 2 t, and d square x over dt square, second differential becomes plus 2, right. So, now if you look at that, we already know a generalized expression, and that says x is equal to c 1 plus c 2 t plus c 3 t square. That is the equation of motion for this particle. Then if I want to find the velocity, I can find c 2 plus 2 c 3 t, and then if I found the acceleration, it becomes 2 c 3. So, this is your definition of position, velocity and acceleration. Now, I need to introduce one more concept, which is about vector, 3-dimensional vectors, and that is where now we are going to look at vector quantities and understand how they work. So, I take an arbitrary point O, and then let us say I go to a point P and a point S. So, I am going to a direction here, direction here. What is the resultant direction? So, this is a vector, this is called vector algebra or vector space. All right. So, now to define that, we can now look at vector as two things. One is the magnitude and the direction. So, if I say this vector is 4, this is magnitude 5, then I can say 4, and if they are going in same direction, plus 5, that becomes 9. So, we are doing vector addition, and if they were, so this is in the same direction. Let us say 4 was going in one direction, plus 5 was going in opposite direction, then you have minus 1. So, I think this is simple way of looking at it. Now, you can look at a 3-dimensional vector. So, if you look at here, and this is an arbitrary point P, and if I join that here, then I have a projection on x y direction. Let us say this is x direction, this is y direction, and this is z direction. So, if you look at the projection of this here, then I have two component, one is in x direction and one is in y direction. So, if I look at that A, let us say this is the A vector, then this is O point. So, A vector is equal to OP, and that is vector in terms of A. Then we are looking at A has component in all three directions. So, that is AX x cap, and I will tell you AY y cap and AZ z cap. Now, x cap, y cap and z cap are unit vectors. So, if I take any Cartesian coordinate system, then I have unit vector in x direction is x cap, another one in y cap, and the third one is z cap. Now, the reason we need that, because once we have unit vectors, then we can very easily multiply unit vector with the 3-dimensional body. So, if you look at we can create different kinds of multiplication, which is between the vectors, vector multiplication, and there we have a dot product, and then we also have a cross product. For the dot product, you can see that you can say it will be equal to A, which is the magnitude of A, magnitude of B, and cos theta between the two. So, if there is A and this is B and this is theta, now you are looking at the dot, what we call as a dot product. And the reason I need to tell you this, because when you have n number of such particles and you have to look at their dynamics, then you are dealing with the vectors. So, now in this case, if you look at the cross product, and we will use all of that in our programming. So, in that case, I am going to come up with let us say this C vector, which is a cross product of A vector multi cross, and with the cross sign here B, then it becomes A, magnitude of A vector, magnitude of B vector, and sine theta, the angle between the two vectors. Okay. So, this is A vector, this is B vector, etc. So, now I am just going to stop here, because I want to just look at a 3-dimensional model. So, now let me just plot a 3-dimensional model and go with that. So, motion in 3D, and the 3D is important because our boxes, if you look at the simulation box, is a 3-dimensional box. Now, I am going to create these 3 vectors here, and now I have particles in it, and I can now define A vector for that. So, there are n such particles, I is equal to 1 to n, and I am now going to look at one such particle with a vector quantity, let us say it is called r at any time t. Now, time factor we can also bring in. So, this is r. So, we want to find out what is the r t. So, if you look at this r t vector is equal to x t x cap plus y t y unit vectors z t z cap, and if I have to create the velocity of that, then x dot, which is dx over dt. So, x dot is equal to dx over dt, and x double dot is equal to d square x over dt square. So, if you look at v velocity vector here, then will become that plus y dot over y cap unit vector z dot over z cap. Now, if I want to take acceleration a t, then it will become x double dot, which is given here, plus x cap plus y double dot y cap plus z double dot and z cap. So, now if you look at this 3-dimensional system in a box, I can go from x, or let us say r I, and this is summation of I is equal to 1 to n, and I can sum that x I t x cap plus y I t y cap plus z I t or z cap, and I can do this summation for all x, y, and z. So, I can have these 3 summation signs here, each one for each kind. So, now if I just create the final system here for 1-dimensional motion, and same thing you will do in 3 dimension now that you understand 3-dimensional translations, then x t at any time equal to x 0 plus v 0 t velocity plus half acceleration t square. That is the generic form. If I go to velocity t, then it is equal to v 0 t with differentiation over x, differentiation over time dx over dt. So, this is dx over dt, that equal to v t v 0 t plus a x t, and the second differential with time, which is equal to acceleration a t is equal to a x. So, this is the formulation that you will put in your program, and we will talk about all these different formulations in a way that we can now understand the computational models that we are going to look at. So, let me stop here, and then I am going to summarize this the section of videos that we have done in the area of advanced statistical mechanics applied to different ensembles, and then we begin with our journey for creation of the computational methods for solving second order differential equation, motion which is the second law of Newton, and then creating the trajectory of each atoms. Thank you.